Hello everyone, welcome back to online lecture series on fluid mechanics and hydraulic machines. Today we are going to begin a new chapter, that is dynamics of fluid flow. So let's begin. In our previous chapter, that was kinematics of fluid flow, in which we were analyzing the velocity and acceleration of a fluid at a particular point without considering any form of forces. So that was the kinematics of fluid flow, and now in this chapter we are going to consider forces that is applied on the fluid, that is the dynamics of fluid flow. And here the fundamental assumption that we are going to make is, first is incompressible flow, and second is non-viscous flow. So this will be our fundamental assumptions for this chapter. And now let's begin our first topic, that is equation of motion. So here the equation of motion will be written based on Newton's second law of motion, that is the force that is being applied in the direction x, that is Fx, is equal to the product of mass of the fluid and the acceleration in that direction, that is ax. So this will be our fundamental equation for equation of motion. And here the forces which are present in a fluid flow, that will be mentioned over here. Forces present in a fluid flow first will be pressure force, Let's denote it as Fp. Second will be gravitational force. Denoted as Fg. Third is viscous force. Fv. Fourth is force due to turbulence. That is Ft. And last one is force due to compressibility. Fc. So these are the forces, and now we can write down Fx as is equal to, let me first put Fg x plus Fp x plus Fv x plus Ft x plus Fc x. So these are the forces. Now first neglecting force due to compressibility, that is Fc. So in such case the equation reduces to this, and this is known as Reynolds equation of motion. Then let's neglect force due to turbulence. F P X. So now in that case we are left with this much equation, and this is known as Navier-Stokes equation. And now let's neglect the viscous force. Then we are left with this equation, and this is known as Euler's equation. So this is about the equation of motion. So let's copy this into our main slide. Now our next topic is Euler's equation of motion. So first we will consider a fluid element. So here this will be the axis and axis of the fluid element, and here let's say this is the direction S. Here there are few forces that we need to consider. Let's first say that this is the length of the cylindrical element here is ds. The force which are present over here is from the bottom we are having P into dA, and here the force it is P plus del P over del S ds into dA. Now the next force will be a weight force, which is from the center of gravity of this fluid element. Here it is through the center of gravity. So this will be rho into V. V will be dA ds. Rho into dV. dV is dA into ds into G. So this will be the weight force, and the angle which is here is theta. The angle here is theta. Okay, so these are the forces which are present, and let me draw a triangle for explaining this angle. Here we will have this as dz, here we have ds, and the subtended angle is theta. So let's equate the forces. So here P dA minus P plus del P over del S into ds into dA minus rho g dA ds cos theta is equal to f is equal to ma. So instead of that, it will be, instead of m we can write down rho dA ds. So this entire term is m, and we can say the acceleration is in s direction is as, so it is nothing but f is equal to ma. Now let's simplify this. So we will be, this pda will be cancelled with this pda, so we will be left with minus del p over del s dA ds minus rho g dA ds cos theta. Now let's have a small discussion on as. So as should be equal to dv over dt. So for that it will be like del v over del s into ds upon dt plus del v over del t into dt over dt. Why? Because v is equal to function of space and time. So this will be like, instead of ds upon dt we can write down simply v. So v into del v over del s plus del v over del t into as. And one more thing here, that we will be assuming this to be a steady flow, as we discussed in the initial part of our lecture. So for steady flow we will have dv upon dt as 0, so this term will not be present. So we are only left with as is equal to v del v over del s. So here we will have rho into dA ds into v del v over del s. So we will be dividing the entire equation with this term. So finally what we will be getting here is minus 1 upon rho into del p over del s minus g cos theta is equal to v into del v over del s. Now we can write down this all together, that is 1 upon rho del p over del s plus g cos theta plus v into del v over del s is equal to 0. Now instead of cos theta, if we see this figure, we can write down it as dz over ds. So here we can eliminate ds from everywhere, so we are left with del p over rho plus g into dz plus v del v is equal to 0. So this is Euler's equation of motion. So let's copy this into our main slide. I think this will not work over here. We will only have derivation into our main slide. So this is end of today's lecture here. Today we started with our new topic, that is dynamics of fluid flow, in which we discussed the equation of motion based on Newton's second law. We obtained different forms, that is Reynolds equation of motion, Navier-Stokes equation and Euler's equation, and in detail we derived the Euler's equation of motion. Thank you for watching this video.